Check, 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 check. Howdy, y'all. Professor Parks, PhD here, and I'm hoping that this finds you all well, and I'm hoping that the audio is fine. It looks to me as if the video is good. I was playing around with a new intro. I don't know how well that worked because it's very large. I made it through Universe Sandbox, and I'm not really happy with it. But hey, it's an intro. I'm going to check my sound real quick, see whether or not. Aha, okay. Looks like the sound's good. All right, anyway, I am Professor Parks, PhD, and I make content on astronomy, science skepticism, and mental health. If you like that sort of thing, please like, share, and subscribe. Now, today I want to share some big news that we have here at George Mason. It was announced a couple of days ago, but I have just now gotten around to getting the time to talk about it. And so, what is the big news? Howdy! And, I don't think I actually have heard your name pronounced, and y'all Irish folks have some weird pronunciations. I want to say it's Roisin, but I am fairly confident I am butchering the shit out of your name. So, but howdy. Welcome. So yeah, big news. So you may have noticed I am wearing my NASA pin. Now, I've mentioned this before, that I have actually never been funded by NASA. None of the, as far as I know, definitely none of my research has been funded by NASA. It has been funded exclusively through the National Science Foundation. So yeah, I've never really been a NASA shill. As far as I know, all of the co-authors that I've been on, all the papers that I've been a co-author on, I don't think any of them have been funded by NASA, although when I think about it, Tabby may have had a Roisin. Ah, thank you. But howdy, Roisin. So yeah, I've never really been a NASA shill before until now. And, let me tell you why. And really my affiliation with NASA at this point is somewhat secondary. Let's see here. There we go. How about that? Yes. Awesome. Now, I chose this particular article for a couple of reasons. What article is that? That article is GMU, George Mason University, the university that I am currently sitting in, that I am broadcasting from, leads a 19.5 million, yes, that is a million with an M, Landalt space mission to study dark energy. Now, I picked this article out specifically because y'all know me. I love honesty. I really have a bone to pick with pop science communication when they overreach. But Irish names, they look like deliberate attempts to mislead innocent people. Yes. Such as that actress Siobhan. I can't remember her. Her name Siobhan. It doesn't look anything like her, how it's actually pronounced. But anyway, back to this. So, we are, Dr. Peter Plavchan put into a proposal some time ago. This is what is known as a Discovery mission. It is a 5-year mission. He has 4 years to develop the satellite and then deploy it into space where it will be geostationary, and we will have a year of science with the potential for additional funding beyond that. Now, what is the Landalt mission? What is it actually going to be doing? Simply put, the Land-Alt satellite is what we refer to as an artificial star. In a moment, I'll talk about how astronomers measure brightness, or how we sort of define brightness. But I will start off by saying that currently, our ability to, our accuracy when it comes to making photometric observations, and photometry is quite literally the measure of how bright something is, our accuracy is around 3%, which for a lot of applications is good enough. Essentially, it allows us to make fairly strong conclusions about a lot of different astrophysical quantities. However, we're getting into the regime that we call high-resolution astronomy. We're getting to the point that our sensors are good enough, our telescopes are large enough, that we are now getting into being able to determine the brightness of something in 1/1,000,000th, or even one part in 1 billion. These are extremely high-precision instruments. So when it comes down to having an accuracy of about 3%, it really starts to be counter. Our increased precision is really kind of wasted because our accuracy is in that context is so large. This affects things like determining the ages of stars, which in turn has direct implications as to how old and thus the structure of exoplanets. I say all this because Dr. Plavchan Peter made his bones in the exoplanetary work. He actually discovered the first exoplanet around a star that had a debris disk. Effectively, a debris disk is the end stages of the planetary disk that planets coalesce from. So that star is called AU-MIC, and he was the first one to discover that planet. I like to call it Peter's Planet, because I likes me some alliteration. Anyway, oh, hello. We got lots of lots of people in the chat. I need to move this over here so that I'm... Yeah, normally with OBS, the chat is pretty visible, but I don't want to... What's going on? Why can't I pop this out? I don't want to miss anything. Oh, that's not what this is. What is going on? I'm assuming I'm still alive. I'm confused because what I was using to monitor my chat changed. Not entirely certain how or why. So, pardon the brief tech issue. Would explain why my comment section seemed to blow up, or my chat seemed to blow up. All right. And they say flat earthers can't tech. And my internet is really slow for some reason. So while that's popping up, what was I saying? Yeah, so Peter made his bones with Exoplanet, which is what motivated this this project. And he realized that we were getting into the point that, given this era of high precision measurements, it really didn't mean much if our accuracy in photometric work was 3%. So he developed this program, or this project, or this idea, and he proposed it to NASA, and they awarded it to us, or to him rather. And yeah, now off we go. And so he has moved off to essentially spearhead this mission. And so I have gotten at least a title promotion. I am now the operations director of GMU Observatory, and I am a part of this project because I am going to be in charge of one of, I think, around 5 ground stations that will be involved in this project. Now, what is it going to be involved in this project? Well, as I mentioned, the Landolt satellite, which is about the size of a bread box, I think it's technically a CubeSat, it will shine a laser down onto the Earth, not really targeting the ground station, but it will be definitely bright enough for the ground stations to be able to see it. And what we're going to do is we're essentially going to be we're going to be observing that light, which has a very set, very precise luminosity, which we know. And then we are going to observe it in every waveband that is possible. We're going to observe it in the near ultraviolet. We're going to observe it in the blue, in the green, in the red, in the near infrared, and also in the slightly longer near infrared. That's at least what we're going to be doing here at George Mason. Now, we're going to take those observations and essentially we're going to calibrate our photometric system such that we can get accuracies far greater, far better than 3%. So we are going to be a NASA facility in a sense, and yes, we are putting up a satellite. So that's pretty damn exciting to me. And again, given that I interact with folks who don't seem to think that space exists, I think, what is going on here? Space exists. I think this is going to be a marvelous opportunity to show at least kind of behind the scenes of what goes on with a NASA mission. Hopefully add a little bit more transparency to the process. And just saw a chat that or a comment that I'm gonna refer to. So add a little bit more transparency to the process, and hopefully people will find it not only informative but entertaining. All right, so Wild Thoughts AI says, Professor Parks, I respect you as an astrophysicist, but how do you justify your belief in God since there is no demonstrable evidence? That is the point of faith. I believe that if there was demonstrable evidence of God, then faith would not be necessary, and faith is one of the cornerstones of Christianity. I believe that the search for demonstrable evidence in terms of God is wrong-headed, both from a physical standpoint and also from a theological standpoint. Because again, if we could prove God exists, then there would be no need for faith. And it is our faith that pushes us forward. It is the fact that we don't absolutely know that there is a reward for us at the end of the tunnel. I find those that claim to be saved and know that they are going into heaven, and so therefore they're going to get the riches of the afterlife. I find that to be I disagree with it strongly. I was going to use a certain word. I was going to say reprehensible, but that's far too strong of a word. Christian faith is about trying, in my Christian faith is about doing whatever I can to bring about the kingdom of God on earth. What that means is doing what I can to create an environment of compassion, of love, and non-discrimination. If that gets me into heaven and eternal bliss, zang. But that's not what I'm looking for. But it is because I have to have faith that means anything. Is the one thing I will say about the show Friends, is they had an interesting show about, is altruism truly altruistic? Are you doing it because you want a good outcome, or you're doing it because you want to help, or are you doing it because it makes you feel good? If you're doing it because it makes you feel good and you're getting a reward for it, does it truly make it altruistic? So I'm not I am not guaranteed of a reward for this. I have faith that my actions will be rewarded at some point, but not to get too long-winded about it, that's my justification for it. Is faith a good reason to believe in something that major in life? Yes, I believe wholeheartedly that it is, particularly in this context. Yeah, so for whatever reason I was mentioning before, the chat usually pops up here in OBS, but I don't know why I didn't do it this before, and so it's down here, so I'm probably going to miss it every so often. But anyway, what we're talking about is the satellite mission. Now, for those of you who don't know, and I suspect a good number of you probably are ignorant of this, is how do we actually measure or quantify the brightness of something? Obviously, the sun is the brightest thing in the night in the sky. The moon is the second brightest, depending on its phase, and then you get into Venus and Jupiter, depending on their locations, and then Sirius is the brightest star in the night sky, and then Polaris, for example, has I can't remember what it is about 100 or so. No, not 100. Is about 5 times dimmer than Sirius, if I got the numbers correct. So how do I know this, or how do we classify this? Well, it goes back to the old Greek dude by the name of Hipparchus. And Hipparchus did a number of amazing things considering the time in which he lived. He was around 350 BCE, and he had very crude instruments, but he had a fantastic sky. Obviously, this is way before light pollution. He was in the middle of bumblefuck nowhere, Greece. And so he had a tremendous view of the night sky. And what he did was twofold. He cataloged the night sky in terms of position, so relative position. So he knew where one star was located relative to others as a function of the calendar year. And in fact, because of his catalog, he was able to detect something we call precession, which has a complete orbit or a complete cycle of 46,000 years. Very briefly, what precession is that the axial tilt of the Earth, which is now currently in line with Polaris, that actually wobbles like a top. So in about 24,000 years or so, Vega will actually be the North Star. For those who have said that the North Star is constant and has always been the North Star, that's actually not accurate. Hipparchus would have definitely seen Polaris moving around a empty spot in space. He was able to, because of his observations, he was able to notice this, and he referred to it as it wasn't the precession of the equinoxes, maybe it was precession of the equinoxes. Essentially, the point of the vernal equinox moved with time. But in relation to this, howdy, Georg, is it possible that you are wrong or spend your life worshiping the wrong god/religion? Of course, of course I could be wrong. That's the whole point of faith, is that I don't have demonstrable proof, but I have a personal relationship with God. I love God, and I choose to believe that love is real, that God exists, and that the moral dictates of the Bible are how I wish to live my life. I am less concerned about what is correct in terms of dogmatic belief as opposed to what is correct morally. So yeah. And in terms of if I die and there is oblivion, and that, my spirit or soul is not eternal, again, my goal in life is to make this world a much better place than it is now. The old adage of leave it better than you found it. Does the fact that my soul is not eternal and gets annihilated nullify that effort? Does it, in fact, make that effort somehow less meaningful? I would say no. So again, I'm not concerned about whether or not I am spending my life believing in a false god or any kind of false deity. And I this is not again, this is not the point of the stream, but I would love to have you on and have a discussion of this, because I'm curious why you find these questions to be important. What made you think that faith is a good reason to believe in God? Faith is not a reason why I believe in God. I believe in God because I have a personal relationship with God. Faith is contingent upon that, is an integral part of that relationship. Hipparchus. So, Hipparchus studied the catalog the stars all over, catalog the relative positions of all the stars that he could see in the northern hemisphere. The other thing that he did was that he decided to come up with a system of brightness, and this was qualitative. What he said, or what he devised, was he said that all of the brightest stars he is going to label first magnitude. Now, magnitude is the term that will continually be reoccurring, in that it is the measure of it is essentially the unit of brightness. He said all the bright stars are first, and then all the stars that he can barely see, he is going to call sixth. And so, because of Hipparchus, when you hear or read that the faintest the human eye can see is sixth magnitude, and trust me, you have to be in a damn good sky in order to do that. Here, I was able to verify what I had suspected, that the faintest star that I can see in the night sky at my location is actually fourth. And so, unfortunately, it's stuck. And what I mean by unfortunately is that it is an inverse relationship. It means that the smaller the number, the brighter the object. In fact, the sun actually has an apparent magnitude of negative 24. Now, how do we know that? How do we get from qualitative measures of magnitude, which is the only thing that Hipparchus could actually do, to a quantitative measure? And that comes in around the mid-1800s. There was an Englishman by the name of Nathaniel Pogson. He decided to throw math at the problem, as you do. And I think it was arbitrary, but I could be wrong. I haven't actually looked into the history of this. But what ultimately came out of it was that Pogson made it a logarithmic system. And he defined that the difference in brightness between a first magnitude star and a sixth magnitude star was 100. And so what that means is that every step in magnitude is about 2.5. So a first magnitude star is 100 times brighter than a sixth magnitude star, but 2.5 times as bright as a second magnitude star. Now that we have this mathematical framework, now that we have a quantitative definition, we can expand outward. We can now define things that Hipparchus could not see. So fainter objects that are now visible, or now becoming visible to Galileo, now to and which now equates to essentially binoculars now at this point, and then further. So that this, like, for example, the faintest that Hubble was able to achieve was, I think, 32nd magnitude. James Webb, I think, is getting down to 34, 36. And so, there is, that's essentially the kind of the brief history of how we quantify. Howdy, Clive. You highly recommend I watched Matt Dillahunty, who was a Christian until age 28 and now an atheist. I highly recommend you watch his debates. He is very strong in logic and philosophy. Again, I have of no interest in trying to prove or disprove God. It is not meaningful to me in any way whatsoever. It is actually, from a theological standpoint, contrary to my intrinsic belief system. I appreciate you mentioning this. I have seen a little bit of Matt Dillahunt's work. Honestly, I would not consider him an atheist. I would consider him an anti-theist. And by that, I mean an anti-theist is someone who not only does not believe in God, but thinks that anyone who does is wrong and should not believe in God. And it is that should not that I have a problem with, and I say verges on fundamentalism. Now, that's honestly, Wild Thoughts, that's honestly the last thing I'm going to say about it. Again, I would love to have a conversation with you at some point about it, and I appreciate that what your questions, I'm assuming, are coming out of a position of concern, that you are not trying to troll me or anything of that nature. But yeah, so thank you. So Pogson came up with this system of measurement. Now, the tricky bit comes into that, particularly when we started getting into the age of, I think they're around the 60s, 70s, may have been a little earlier. I honestly don't remember. But we got these things called, we got photometric plates. So I guess much earlier than that. And from photographic plates, we were able to actually start quantitatively measuring how bright something is on a plate. So basically how much silver nitrate was exposed or basically turned black. We were able to turn that into a magnitude, turn that into a function of brightness. The more that turned black, the brighter the object was. But the problem comes in is that not all optical systems are the same. In that, and actually, I would contend that no two optical systems are identical. Even if they were the same telescope designer, same aperture, with the same filters, with the same camera, you're going to have manufacturing defects. They are going to be different in one sense or another. Sometimes the difference will be very small. Other times the differences can be very large. And so what needed to happen was there needed to be some way of standardizing the intensity that we measure with the optical systems that we're using. And so the first person to do this was a gentleman by the name of Arlo Landau, who I had the distinct honor and pleasure of working with at Louisiana State University. Here is him back in circa 1960 with the telescope that he used to do his fundamental work. Arlo is a character. He loved puns, and he actually, I think in 1956 or something, some kind of geological society basically had a program where they would send scientists down to the South Pole, specifically the South Pole Station, so they could spend a summer there doing whatever it is. And Arlo was one of them. Arlo's not a geologist, so I don't remember what exactly he was doing down there, but he would regularly give talks to the new students about his experiences down there. Fabulous. Unfortunately, we lost Arlo a few years ago, but this is the legacy of his work. So what Arlo did was he took this particular camera, which I believe is a Schmidt camera, and he took a particular set of filters, which are now known as the Johnson-Cousins system. And he came up with a way of standardizing what these magnitudes were. Now, incidentally, this system the system is basically hung on, or is the signpost is the star Vega. So basically, the star Vega is defined as having an apparent magnitude in across the board of 0. So it is defined as 0. It is the pinnacle standard star. And so from that, Arlo was able to then take the intensity from Vega and then basically compare that, use differential photometry essentially to come up with what he called his standard fields. Now, let me see if I can. Let me see if I can show you what one of these standard fields looks like. So many windows open. So much high IQ research. What is this thing called? I actually used these fields myself, and I don't know what's going on with my computer, but it is very slow. There it is. All right. Finding chart blank. Okay. I need a new computer. Holy crow. It's so slow. Probably because I have so many damn windows open. Finder. I may have to forego this because I can't seem to find it. Finder chart. There we go. All right, transition. There it is. So this is a finder chart. So all of those stars. Again, this is an original photographic plate that Arlo took. All of these stars labeled G, T, E, B, blah, blah, so forth and so on. He was able to, using Vega as a signpost, he was able to define or basically calculate or measure, as it were, the apparent magnitudes for all of these stars. And that is the start of photometric calibration, which at the top of the stream I mentioned is currently sitting around 3% accuracy. I mention all of this because, one, you need a little bit of background to understand what the Landolt, or why the Landolt mission is doing what it's doing, and also why it's named after Arlo. Again, I had the honor of working with him. Great guy. And I am sorry that he is no longer with us, and certainly sorry that he is not able to see the fruits of his labor. Now, what did I want to show next? Now, actually, I am going to go back because there was something. I made mention of why I don't. That particular article that I brought in, or that I showed at the very beginning. Chrome, GMU, where is it? That's not it. I can't seem to find it. Let's go with that. That's not right. How about if I can do this? Can I do this? There we go. I can do that. Awesome. Here you go. So, it states GMU leads with 19.5 million Landolt space mission to study dark matter. That's not accurate. It has the Landolt mission because, so, the Landolt mission is attempting to improve the accuracy of our ability to measure light and our ability to quantify how much light something is putting out. That is going to affect all of astronomy that relies on photometric observations. Dark energy is one of those aspects. The observations that led to the formulation of dark energy, that illustrated to us that the universe was actually accelerating outward were observations of Type 1a supernovae. These are white dwarfs that go supernova when mass from a binary companion, dumps a whole lot of its mass onto that white dwarf very quickly, or relatively quickly. It explodes once it gets to a certain mass, and it is one of the second most energetic phenomenon we observe in the universe, and so we can see it from a very, 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 very far away, long distance, and so we can use that to map out what the earlier universe was doing. And the Type 1a supernovae are known as standard candles. Now, a standard candle is something where we know the luminosity of the event absolutely from a different technique. We understand that Type 1a supernovae, all of them explode basically the same way. They put out exactly the same energy. It doesn't matter what the mass of the white dwarf was originally. It doesn't matter how much mass, the mass rate that was being dumped on it. It doesn't matter what the composition is. Basically, all Type 1a supernovae are identical. That allows us to be able to determine distances by studying how bright it is. So to first order, the brightness of something is based on two factors. It is based on the intrinsic brightness of an object, its luminosity, and its distance. And so if you know the intrinsic brightness of something, which we can from Type 1a supernovae studies, and we can measure its brightness, then bing, bang, boom, we get distance. But that distance is dependent on how well we can measure the brightness of something. And if the brightness of measurement or brightness of that supernovae only has an accuracy of 3%, that has implications to the distance of that supernova, which in turn has implications as to where that star is and how the universe was expanding at that time. So it will be vital if the space mission is successful and we are able to significantly increase the accuracy of our photometric standard system. I should say that when I talk about the 3% accuracy, what I mean is the accuracy of the photometric system of basically being able to relate one star's relative brightness to another. That is where that error comes in. And so if we can damp down that error to make it more significant, then James Webb, for example, and Euclid, for example, their observations can be made much more precise. And so that will lead to a better understanding of dark energy. Or at least it will lead to a better understanding of the positions, the distances of Type 1a supernovae, which have a direct implication or application to dark energy. But, oops, that's not what I wanted. But Landolt itself will not be studying dark energy specifically, because as I said, this mission was developed by Peter in regards to exoplanet research, because we have an adage in exoplanet research that basically says you cannot know the planet. You know the planet as precisely as you know the star that it's orbiting, because a lot of the characteristics of the planet are in relation to the characteristic of the star, including its size, its rate, its temperature, its luminosity, and its age. And so that is determined one way to determine those characteristics is photometrically. And so again, if you have errors in, say, how large the star is, then that error is going to translate into how big the planet is based on this technique called transit method. And this all goes into confidence. When I said earlier that there is a planet going around AU-MIC, I say that because we have, from the measurements and the errors associated with those measurements, we have confidence that the signal we are detecting is from an exoplanet. The better our errors, or rather the smaller our errors, the more confidence we have in making these claims. So, okay, I don't understand your meaning about causality, but so yeah, that's basically what's going on here at George Mason. We are going to be. I think I'm buffering like a motherfucker. We are now home to the Landolt mission. Like I said, our observatory is going to be a ground station that will contribute data that will ultimately be used to better define our magnitude system. I said before that I use Landolt standards. The way that we do photometry, you can do it one of two ways. The primary method is what we call differential photometry. Effectively, what we state is that the field of view of your camera is small enough such that all of the stars can be thought of being viewed through the same atmosphere, same quantitative description of an atmosphere. So therefore, the effects of the atmosphere on any particular star is not different from one star to the other. That's differential photometry. Pretty easy. But if you want to know what the actual apparent magnitude is, and in this way, this is where distance comes in. You need to know what the actual apparent magnitude of a star is, or any object that you want to use in order to determine the distance to something. You have to use absolute you have to use absolute photometry. You know, with the flat Earth debate, particularly in terms of perspective and sun setting and all that kind of good stuff, or no, seeing too far. We talk about atmospheric refraction. Now, astronomers deal with atmospheric refraction, or at least photometrists deal with atmospheric refraction quite a bit, but in a different way. Atmospheric refraction, comparatively speaking, displaces a star to a very small degree. And so that small degree does have noticeable implications on the Earth, but from an astronomy point of view, the position of the stars changed is not relevant to photometrists. Now, to an astrometrist who is decided on measuring the exact position of a star, then atmospheric refraction comes into play. But from a photometry point of view, what the atmosphere does is two things. In general, it causes extinction, or atmospheric extinction. Photometric extinction. What that means is that it causes two effects. One, it causes the actual measured brightness of something to be diminished than from what it actually is. So the apparent magnitude of a star is a function of altitude. So if you were in the ISS, you would measure a star to have a certain apparent magnitude. But if you're on the ground, the apparent magnitude of that star is different. Now, I stated that you would expect that to be distance dependent, but not to that extent. The distance between the ISS and the ground is essentially negligible. You would expect the apparent magnitude to be the same if the atmosphere didn't do this extinction business. The other thing that it does is that it causes the star, or any object, to become redder, because the atmosphere will block out more blue light preferentially than does red light. This comes into play because I mentioned before that astronomers, the photometric system is broken up into effectively wavelength, color, frequency, however you want to look at it. So, for example, this Johnson-Cousin filter set that we have is U, which is in the very near ultraviolet, B, which is in the blue, V, which is in the green, R, which is in the red, I, which is in also just red and very, very near infrared. the color of something or the temperature of something is going to dictate how bright that object appears in those particular wavelengths. So, for example, a cool star or a cool object, something around 3000 Kelvin, for example, is going to appear very, very red. Something that is 30,000 Kelvin is going to appear very, very blue. So the magnitude will vary as a function of filter. So, because of this color effect with extinction, the atmospheric extinction, that's going to affect the colors of things. So, or the magnitudes in particular filters. So this is an effect that we need to get rid of. And the way to do that is, because Arlo spent so much time and care in creating these standard stars, we know what these stars, their apparent magnitudes are. And so we will observe these standard stars over a course of a night over varying different altitudes, which is this effect is a function of altitude. The lower you look down on the horizon or towards the horizon, the more atmosphere that you're seeing through, what we refer to as air mass. And the worse your extinction and the worse the color preference towards red is going to be. And so you need to be able to, so absolute photometry is using these Landau standards to basically to get to the apparent magnitude as if the atmosphere does not exist. So for us, for astronomers, for photometrists, that's what the atmosphere, that's the pain in the ass that the atmosphere has, is not so much that it changes the positions of things, which it does, but it also changes the brightness and coloration of things. How much do you think that the popularity of religion, Christianity, influenced you in a way that makes you believe you have a personal relationship with God? Also, do you think everything is true in the Bible? I know I said I was going to drop this subject, but no. If you follow any of my channel, I have vehemently stated multiple times that I am not a Bible literalist. I believe that the Bible should be taken as allegory and not as a literal testament of what happened in the past and science in general. The historicity of the Bible has been clearly demonstrated to be false. The science behind, say, Genesis has been demonstrably shown to be false. So there is no way for me to be able to reconcile that evidence, that academic evidence, with being able to take the Bible literally. Plus the fact that there are inconsistencies with the Bible itself. So yeah. Yeah, that's all I'm going to say on that. Again, I will say, all right. Wild thoughts. Again, I will put it to you if you want to have this conversation on stream, or just through email or on Discord or however you want. I would be happy to have the conversation with you, or really anyone else, Christian or otherwise, because I also have issues with fundamentalist Christians, particularly those among the flat earth community who think that the Bible needs to be taken literally in order for God to exist. Again, I have theological problems with that. But so yeah, there's that. So back to that, and really, I guess at this point, I am done talking about giving you the update on the Landau mission and how I am now a NASA shill, as it were. One thing I also did want to point out is that if for those of you out there who are basically stating that, Peter is getting rich off this, NASA is giving him $19.5 million. And that's not actually accurate. What NASA is doing is it is giving Peter management over the $19.5 million. But Peter has to be associated with an organization in order for NASA to give him the money. This organization in particular is George Mason University. Now, the way that universities work in terms of research is that there is something called overhead. And I believe that this is a large problem within academia that we address very, very little, because from an academic perspective, I don't think we have a lot of power for change. So, whatever money you bring in if you get a grant, say you get a grant for $1 million, and you bring it into a university, first thing that happens is that the university takes its cut. And that cut is enormous. I actually just got educated. When I was doing active research, the cut, depending on the university, was anywhere between, say, 45 to 55%, or actually about 45 to 50%. That's right, folks. There are certain institutions back when I was doing active research that if you brought in $1 million, 500,000 of it went to the university and not to your research. And they refer to that as overhead. Basically, there is the overhead comes to the administration of the money. So there are strict rules as to how a researcher can actually spend grant money. And that is also kind of problematic because it is very compartmentalized. When you put in for a budget, you have to budget, this is the amount of money I'm going to give to my personnel. This is the amount of money that I'm going to give to the telescope or the instrument that I'm going to use. This is the amount of money that I'm going to set aside for publications, because we have to pay to publish our results unless you publish in MNRAS. Then it gets into the weeds of, this is the amount of money that I'm going to pay for furniture. This is the amount of money I'm going to pay for computers. And if you, for example, overspend on computers and realize that you need an extra hard drive, but you underspent on furniture, you can't take money from the furniture section to pay for a computer, even though it is your grant, because you did not specifically allocate the money for that to be computer use. You can't buy it from the pot of money in furniture. So yeah, when folks accuse academics of being in it for the money, it's fucking laughable. It is completely laughable that we get you hear that we get these $20 million grants. Well, half of that money is going to some organization to basically manage where we can spend the money. And the only perks that we get out of this is that there are monies set aside for conferences. And yes, sometimes those conferences are in lovely locales like Honolulu, but sometimes they're in even lovelier locales like Long Beach or Dallas. So I guess you could say that our perks are we get our travel reimbursed going to various conferences. So yes. Oh, thank you, Maya, and howdy. Thank you. Like, share, and subscribe. Wild thoughts. Will I do more debate with flat earthers? I would like to. I would like to have conversation with flat earthers. It's just I haven't had them really approach me to do it, and I really haven't had the time to approach them. I've reached out to a few. I was most excited about talking with Dr. Bennett, but that didn't really work out. I'm still waiting to talk to Lucky Hawkins. He was over the spring. He had I think he has children that are in hockey, and so his priorities was that, so he didn't have the time. I need to reach out to him now to see if he has any time to get on there. I wanted to talk to Space Audits Alan, but that I actually bailed on him because I didn't have the time. So I want to talk to him. I also want to talk to Toby from the Aether cosmology community. I wouldn't mind talking to Austin again, but I'm hoping that it would be as cordial as the last time I spoke with him. And honestly, that one I would be interested in actually having more of a theological discussion, because I know that his beliefs do stem from his Christian faith, and he has made some, in my opinion, troubling statements, such that he is a prophet of God whose mission is to bring flat Earth to the world. And I'd like to discuss that with him. And then finally, I have started to engage with Flatzoid. At first, he thought I was a geocentrist, but when I corrected him on that, I think his enthusiasm for talking to me has waned. But he has definitely offered that I can come onto his show and have a conversation with him. But since I don't really know when he actually goes live, because I haven't really looked into it, I don't know when that's going to happen. So, let's see. Do people think that gets paid directly to you? Yeah, yes. I have spoken with flat earthers who basically say, you're getting millions of dollars from NASA or whatever. That's not accurate. Yes, there are obviously there are multi-million-dollar projects, but really for example, Peter is bringing in $4 million to George Mason, and George Mason, well, I'm not going to get into the weeds of that, but that $20 million, $4 million is going to George Mason. The rest of that is going to our partners, such as I think it's Blue Canyon, who is going to be actually being responsible for creating the actual satellite itself, and I think deploying it. I'm not entirely certain. That's, like I said, years away from it. You don't have to talk to Flurfs. I only expect you more. Really, when it comes to flat earthers and science skepticism, I know I say science skepticism, and I would be interested in talking to people who deny climate change and also 5G, although 5G really isn't my field of expertise, and climate change is only kind of in my wheelhouse, but I wouldn't mind talking to them as well. Not really going to talk about vaccinations, because I'm not a biologist. I'm not an epidemiologist. I have nothing really meaningful to say on that. When it comes to evolution denial, again, I'm not a biologist, so I don't have anything really meaningful to say about that. Other creators, such as conspiracy theory, conspiracy cats, and Professor Dave, they would do a far better job at doing debunking than I do. What was I saying with that? I would love to have discussions with them, not debates, because honestly, I'm not interested in trying to prove anything to anyone. My main goal in life, or at least professionally, is, well, really everything, is education. I want to bring what I believe to be true to the masses, or to whoever will listen. And again, my expertise is in astronomy. I often will make posts like I did today about, bigotry that I see among the flat Earth community. But the main reason is I want to understand folks. I want to understand where they're coming from, why it is they have the beliefs that they do, because I think the only way that beliefs can be changed is through a mutual understanding and through trying to understand why people have certain conceptions or misconceptions or whatever, and then working through with polite and meaningful dialogue. So that's why I talk to people like that. Now, I will start. I do want to mention something else. if I can find it. How about if I do this? Haha. So if you've been following my channel, you will know that I let's see here. Have been doing a bit of an experiment with my snazzy Sea Star, which my lovely patrons, one in particular, helped me purchase. So, thank you. Not entirely certain if they want to be recognized or what, but I will thank them anyway. So, let me readjust things. So the experiment that I'm doing is I'm taking observations as frequently as I can of the sun using the Sea Star telescope that I have. And I wanted to, whoops, that's not what I wanted to do at all. This is what I wanted to do. Oh, darn it. It's me not being able to tech again. You know, when I become rich and famous, I will be able to hire someone to do this for me. Won't that be lovely? Here we go. So, it's the dream. So what I'm doing is, again, every day that is clear and every day that that fits in my schedule, I take an observation of the sun using my tiny Sea Stars telescope. It is a beautiful instrument. I love the hell out of this thing. And what I do is I basically measure the apparent size of the sun in both height and width. What I'm attempting to do, the point of this, or at least the original thesis, was to demonstrate that the angular size of the sun changes as a function of year, because with the heliocentric model, the idea in the sun is at the center of, roughly speaking, at the center of the solar system, that the Earth goes around in an elliptical orbit, that there is a 3% change in the distance between the Earth and the sun, which I think it's an 11% difference in the size. Honestly, I don't really remember, but it's measurable. It's a 62 arc minute difference between when the sun is close, when we are as close as the sun, and when we're farther away. So I did some initial calculations, and I figured that my plate scale was around 2.4 arc seconds. And what that means is that I can, with that minimum error, I can certainly detect a difference in the size of the sun to 62 arc minutes. Whoops, that is not what I wanted to do. Yeah, we'll do that. I can't see the chat anymore, but I will cope with that. I will take this off in a second. So I've been measuring the sun. I've been measuring the size of the sun and converting it from pixels into arc seconds. And so you can see here the blue dots, and hopefully you can see here the blue dots are the width of the sun as I measure them, and the blackish, darker bluish dots are the height of the sun as I measure it. And you can see that there is a distinct trend. Even I apologize, the Excel is really bad at being able to plot error bars. But again, the error bars are in the range of 2 arc seconds or so, 2.5 arc seconds or so. You can see that I am seeing a dip of about half an arc minute, 30 arc seconds or so. So again, this trend is statistically significant. I've plotted a couple of thread lines through it. One of them is a linear fit. The other one is a power fit. Linear seems to be the best fit, even though from an astrophysical standpoint, it shouldn't exactly be linear, but the time frame may not be long enough. Now, what I find to be encouraging about this is that in the northern hemisphere, we are further away from the sun in the summer than we are in December or in the winter, this tracks. What I am seeing is a definite decrease in the size of the sun as we move towards June. Now, this is the dates specifically are from, I believe, the end of March through April. I have data through May, and I have data for the beginning of June that I haven't been able to analyze yet. I'm hoping that I can see this. What I'm really hoping is not only will this trend continue, but I'll actually see the trend bottom out. That it will get to a certain minimum size or a certain size, and then that trend will reverse itself. And so to first order, my goal, which seems to be succeeding, is to demonstrate that the size of the sun does in fact change. Come on. As a function of calendar date. And so one of the things that I have not been true to my word on is I have all this data and I have the images specifically, and I want to make them public on my website so that anyone can download them and anyone can do this analysis so they can see it for themselves. Again, I want to be as transparent as possible with this experiment because I know, at least in certain views of the geocentric model, from what I have now discovered with the Tychos model, is that the claim is the Earth is kind of sort of at the center, but you have circular orbits and uniform circular motion. And so this would essentially be evidence to refute that, because what I'm really hoping to be able to do is I'm hoping to, once I get a complete year, I will be able to fit basically the Earth's orbit around the sun, around it, and get an ellipse that would indicate a difference of 3%. I don't remember off the top of my head what the actual eccentricity of the Earth's orbit is. I think it's like 0.011, but that's what Google is for. But yes, I'm hoping to be able to reconcile that. One of the other things that I want to be doing that's on my kind of priority list with this project is I want to use Stellarium to get the expected value. What is the expected size of the sun on these particular dates, and see how well my observations match up to them, and basically compute something known as a percent error. Because yes, I am seeing a trend, but it could be that my dates or my sizes are too small, too large, or what have you. You may have noticed that those two lines are actually offset from one another. What that is telling me is that the sun is wider than it is than it is tall. It's wider than it is tall. Because of various factors, which I can go into later on, that shouldn't be the case. Now, it is true that the sun is squashed. It has a certain obliquity. The polar axis is smaller than the equatorial axis, or radius, diameter, what have you. While that is true, I don't know whether or not I would be able to measure it. And given the angle of the axis, I would not be able to see. This trend should not exist. So what that tells me is that I have a systematic bias in how I measure the height and the width. And I point this out because, again, I loves me being as transparent and honest as I possibly can. I am illustrating that there is some kind of bias in my observations when it comes to the size of the sun from height and width. It does appear as if that bias is being corrected. That bias is getting smaller over time, but I haven't quite figured out why that bias exists. And when I do, then I can take steps to rectify it. What is the best demonstrable evidence for curvature? I think it is the sunrise in one city is a sunrise in a different city. Anything better? So when it comes to curvature, I would say, again, I would check out MC Toon's channel. I would check out Mr. 42. Who else would I check out? MC Toon, Mr. 42, Blow Marvel Science. Yeah. There's someone else. There's another creator that I would check out. Early Conspiracy Cats. I would do that. Obviously, there's Simon and Dan, so forth. But to answer your question, I would say that some of the best evidence of curvature are the altitudes of Polaris as a function of latitude. Observations of the height of a star during the solar. That's it. I can science that. Sorry, Matt. He did a set of observations during the summer solstice, and the altitudes of the stars match up very well with a curved Earth. You also have reciprocal zenith angles. Basically, if you measure the zenith position or the zenith direction at two separate locations that are well spaced from each other, you can see a demonstrable angle between them. My kind of personal favorite is the long distance circular. Basically, the sum of the angles, the sum of internal angles of a triangle over a large enough space of the Earth's surface do not add up to 180. They actually sum to a greater than 180. So that's spherical excess. That's probably my favoriteest for some reason, and I don't know why. Maybe it's because I have a secret hatred for triangles, and seeing them, get bent is, I don't know, some kind of kink for me. I honestly don't know. Let's see. Stephanie McGuire, but that's not the proper definition. Like, what definition is she talking about? Did I miss that? I must have missed that. So yeah, that's what's going on with that. Where did I want to go next? Oh, the last thing I wanted to do was one of the things on my bucket list is to basically have astrophotographs of every object in the Messier catalog. At least. And because of the Sea Star that I have, and because I put in a grant and got money to buy an EV scope, I made, just last 2 days, I have made more progress in doing this than in any other, than all of before. So I'd like to show you some of the images that I've taken. They still need to be processed in the sense that I think I can make these images pop more, if the kids still say that these days. So this is nevertheless, that is what most of us were taught in school. Center of the solar system. Yeah, not sure what. There is. Yeah, I'm not seeing Stephanie's comment at all. Yes, and again, I have also been fairly transparent in that I realize that the way certain things are taught, particularly astronomy and from a physics standpoint, there are shortcuts made. So when you were younger, we basically, the teachers will tell you the sun is the center of the solar system. That's not true. That's not accurate. What is accurate is that the center of the solar system is the barycenter of all of the massive object, all of the barycenter of all of the things that are orbiting around each other. But essentially, that's where the sun is located. So it's just easier to say that everything orbits around the sun as opposed to everything orbits around the barycenter, because then you have to start defining what the barycenter is, and that goes into the center of gravity of things, and for an 8-year-old, that's a lot to take in. So yes, there are certain things that were taught as we were as children that were not precisely accurate, but close enough. Anyway, what we're looking at now is M57. It is a ring nebula. Howdy, Norman. This is M57. I seem to be lagging quite a bit, so I don't know. I don't know where I am with things in terms of what you guys are seeing. There we go. So this is M57 is a planetary nebula, is a ring nebula. This is essentially what the sun is going to look like, we believe, in about 4.5 billion years. The Earth will no longer be around, so hopefully we will be an intergalactic civilization very much like in the Foundation series. What else do we have going on? We'll flip through these. This is M33. This is the Triangulum Galaxy. Triangulum Galaxy is very faint. It is what we call a flocculent, which is a fun word to say. A spiral galaxy, meaning that it has spiral arms, but they're not very well defined, and so it gives a much more diffuse look. And so with the light pollution that I'm dealing with, that galaxy is not very well, doesn't pop very well. There's Saturn. This is their 4 times digital zoom. This is the C-Star is a lovely instrument, but it is not a planetary imager by any stretch, because it has a very wide field of view. To demonstrate, this is the Andromeda Galaxy. It is a spiral galaxy. It is the closest major galaxy to us at about 2.5, 2.7 million light years away. It is a bit bigger than us. You can see this dust lane. It is a spiral galaxy, but we're seeing it edge on. This is a dust lane. This is basically indicates where, if you see dust, it's a pretty good indication that you're also going to form stars there. Not always, but it's a pretty good indication that you're going to find the formation of stars. This field of view is about a degree in size. And so given that Saturn is probably, I think it's around 12 arc minutes, that's why C-Star is not a very good instrument for that purpose. This is M56. It is a globular cluster. It is a really small globular cluster, and because of reasons, I was only able to take a paltry 2-minute exposure on it. Here is, I have done a little bit of processing, basically adjusted the brightness and contrast so that the stars come out more. M56. This one I really like. And I need to fix this. Hold on a second. Let me transition back to here. Oops, that's not what I wanted to do at all. There we go. Much better. So this is M8, or the Lagoon Nebula. This is a nebula that is in the basically near the galactic center. This is a mission nebula. It is, I believe, a star-forming region, but it's one of, again, this is not really doing it justice. On this screen, it is much, much prettier. There's a lot more detail, but hopefully you can translate all of these images. One of my goals for this for tomorrow is to actually get all of these images up on my website, profparksphd.net, so that people can see them. This is M17. This is the Swan Nebula. Why it's supposed to look like a swan? You got me. I don't know. When people when they name things, very few of these nebulae and star clusters actually look like what they're named after, at least in my view. Horsehead Nebula, bang on. North American Nebula, bang on. Swan, okay, sure. But I think it's very pretty. This is the Dumbbell Nebula. It is the first nebula to actually be discovered. It was discovered by William Herschel, and even though he knew that this has nothing to do with a planet, he named it a planetary nebula anyway, because in his telescope he could not discern any detail, but he could discern that it was a disk, and the only other type of object that looked like a disk in his telescope was a planet. Again, very much like the ring, this is approximately what the sun is going to look like in about 4.5 billion years when it basically shakes itself to death. More ring. More ring. I'm hoping to be able to combine all that ring data. Oh, here's the sun. I've been a little bit lax in posting this, the sun today, happy national, yada yada. So this was yesterday, but so there are those. But those are not all. Those are the sea star images. Some of these sea star images. But I also. Here we go. Hello. Here we go. This is M51, and yet again, I'm going to have to transition over. Oh, I could probably. No, that's not going to do it. There we go. That works, I suppose. So this is M51. These are two galaxies that are, this is the Whirlpool Galaxy. You can kind of see that it's a whirlpool and that it's a face-on spiral. And this thing, in a way, is kind of spiraling down the drain. It is actually being currently destroyed by the larger galaxy gravitationally. It is the gravitational influence of this galaxy is the tidal forces are quite literally ripping the smaller galaxy into bits. Stephanie asks, have you thought about comparing pixel size of the moon to pixel size of the sun? The pixel size of the telescope is, or rather the sensor, isn't going to vary with object. Now, what I can do is I can look at the moon, and which I have done with the EV. I don't know if I do have observations of the moon with the sea star, but they're a while ago when I first got it. I can double check with that as well. I can apply the pixel scale to the image of the moon, and then find out what the angular size of the moon was on that date and see if that makes sense. So I can do that. Are we seeing increased solar activity this year? In a way, yes. So right now we are in a, which is good for me, because while I'm doing this, not only am I getting to take observations of the size of the sun, but I'm also getting to see the sun change with the sunspot, so it's very spotted. So I'm also hoping to be able to use that data to illustrate, or at least to first order, be able to measure what we refer to as the Carrington rotation period of the sun. The sun is a differential rotator, meaning the equator has a period of around 24, 25 days. Near the poles, it actually has a rotation period around 30. If you average that all out, you get what is the Carrington rotation period, which is around 27 some odd days. And I'm hoping to be able to actually use sunspot motion to measure that with a particular error bar. But it and so yeah, the problem with that, it gets a little tricky to do that. because one, you really need a low cadence. High cadence? High cadence. You need observations at least once per day. Ideally, you would like multiple observations over a single day just to have more data. And then on top of that, because the sun is a sphere, tracking the motion of the sunspot as it gets closer to the limb becomes problematic because of foreshortening. So, yeah, I'm not entirely I think I can do it. I'm confident I can do it. What I'm not confident about is how well I can do it with the data that I've got. What is the current model's name for the solar system? No, it is. We astronomers really do not define it as heliocentric. The model I am most familiar with is the modified Nice model, which was a model developed, as you might have guessed, in Nice, France by astronomers there. I don't know why it's named after the place as opposed to the people who made it, but I guess maybe there are a lot of people, and Nice is, nice. So yes, the current model is the Nice model. If you want to label things, it's definitely not the heliocentric model. It's certainly the universe cannot be. When we talk about the universe as a whole, referring to it as the heliocentric model doesn't make a lot of sense. Let's see here. I wouldn't even call heliocentrism a cosmological model at this point. I mean, it was. I agree, Clive, that it was a cosmological model, prior to the 1900s, prior to the discovery of spiral nebulae. But at this point, to say that the heliocentric model is a cosmological model doesn't have the same scope. I mean, the universe is far larger than the heliocentric model, and as I've talked about before, the fact that the Earth goes around the sun, or rather the Berry center of the sun, Berry center of the solar system, you can stick that in any number of different cosmologies, from steady state to Big Bang to possibly Mond or what have you. So, the formation of the solar system really has, or the overall cosmology of the universe has very little impact as to how the sun came about, how the solar system came about. But that might be pedantic. But anyway, more pretty pictures. We like pretty pictures. That's the non-EV scoped, trademarked. Yeah, I was trying to get better images of so I have a lot of images of those. This is M12, a globular cluster. Globular cluster is, as you might expect, named because it is globular in shape. These are clusters of clusters of stars, typically on the order of hundreds of thousands, possibly even a million if you look at M13. And these are believed to be the first, what I would consider to be coherent structures. They are definitely the first star clusters that formed in the galaxy. And so these are some of the oldest things. These are the oldest things within our own galaxy, and they are pretty old in respect to the universe. And prior to WMAP, globular clusters actually played a role in the discussion of how old the actual universe was or is, because some models, depending on if you take a very small, I think I've got this right, if you take a very small value of the Hubble constant, you get a very young universe, young meaning like 8 to 10 billion years, and these things have been measured to be, through an independent way, to be like 10 to even 12 billion years old. So they were so one of the problems with those early small Hubble constant cosmologies was that there were structures in the galaxy that were older than the universe itself, which obviously is, problematic. You were taught an infinite universe. Okay. I don't know if I was ever taught an infinite universe. There's basically, that is still very much of an open question as to. Clive would definitely know more about this than I do, but from my understanding, yeah, I don't believe the universe is actually infinite. So I believe it is. I believe it is finite and unbounded. You can. I don't know if you can. Can you circumnavigate? You'll definitely never hit a wall, is what I'm trying to say. But there is a certain the mass energy of the universe is not infinite. There is a set value. There is a maximum value to the mass energy of the universe. That is my understanding. At least that is the consensus at this point. Although you start getting into multiverse stuff and other kinds of things which are not provable or not. Excuse me. Not there's no way to test that hypothesis. So that is where I'm going. The Ring Nebula, as seen with the EV scope. The EV scope and the C star are very similar in design, in that they are they're essentially just a really snazzy camera. The difference really between Unistellar and C star in a functional way is the Unistellar has a 4-inch aperture, whereas the C star I think has a 1-inch aperture. So the Unistellar can collect more light. M101 Pinwheel Galaxy. Again, while I am getting these images, I still want to play with them a little bit to bring out some of the detail. But at the very least, I have these images of these Messier objects. M56, which is another globular cluster. You can see that in this presentation, it really, kind of blocks off a lot of the background sky. This particular globular is in the Milky Way, is seen in the disk, which is why it has such a rich star field around it. There are many, many more stars in the disk of the Milky Way than there are on the above and below. I am becoming more and more of a fan of rich star fields. This is the star Albireo, which is a binary. I was testing to see whether or not I could actually image the two stars in the binary of Albireo separately. Not so much. Here's the big orange primary, and then the smaller blue star is right there. You can kind of see it poking out, but can't really see it as two separate. It's not resolvable. That would be a case of two objects that are visible but not resolvable. Here is the Eagle Nebula. If you have seen any images of Hubble, you are most likely have seen the pillars of creation. Those are in the Eagle Nebula, so they are right here. I don't think I can zoom in. Oh, I can. There it is. So yeah, you can compare this image to Hubble, and you can see that they're basically the same. Yeah, I don't know why they spent $1 billion to make that telescope. I can do just the same in backyard. So yeah, that is the Eagle Nebula, or M16. We have M94, which is actually, this is the Sunflower Galaxy. So this is the heart of the galaxy. This is the nucleus of the galaxy, or the bulge, the bulge of the galaxy. But the spiral arms are not visible, so it looks more like an elliptical. So it looks like, so what we're seeing is essentially the central part of the galaxy, but none of the arms. So basically what that means is I need more data. You always need more data. As an astronomer, you need more data. Mo data is mo beta. There you go. You can kind of see some kind of central spiral structure in here, but yeah, there's just not enough data there to make that claim. M94. This is a M21 is a open cluster. Open clusters are clusters of, so globular clusters are globular because there are so many stars there that gravity has arranged them into a spherical shape. Open clusters are far younger. They are typically on the order of millions of years old as opposed to billions of years old. And they number in the few thousands. And so there's not enough gravity there to actually get them into a spherical shape. So they are irregular in appearance. The reason why they're called open clusters is because unlike globular clusters, open clusters are not gravitationally bound. So these stars will eventually disperse out into the universe given enough time. This is the Trifid Nebula, which apparently is some kind of man-eating flower or something. I don't know. M20. There's another picture of it. This is M65. Oh, this is the Sunflower Galaxy. Here's a better image of it. So, yeah, again, not really seeing the spiral arm structure, but this is the nucleus of it. These are effectively real color, or true color. These are very close to what you would see if you were in the Starship Enterprise and you happen to look out a porthole, look out the window. Now, because I have not fiddled with saturation, I have not fiddled with any kind of color balance or anything of that nature. The only thing that, and I don't even know if I've processed these. The only thing that I have done when I've processed anything is to adjust the brightness and the contrast. So these are, unlike Hubble images, these are basically true color. Sunflower Galaxy, many attempts at getting it right. Haha, this is the Great Nebula in Hercules Globular Cluster. This one is M13. It has, we believe that has basically a million stars within it. The reason why and that is the reason why it appears so prominent as opposed to those other globular clusters that I was showing before that were really small. Those only have a few 100,000 members as opposed to the millions, or roughly million that the globular cluster did here. And this is a great illustration of the principle of when you look at the Milky Way galaxy, if you're fortunate enough to live in an environment where you can see the Milky Way galaxy, the reason why it looks milky is because you are looking at stars that are detectable but not resolvable. And so you have a lot of stars that you cannot resolve as individual points of light, and they mesh in order to make this kind of glow. And you can see that also is evident in these globular clusters, is that this glow, this background glow, these individual points of light seem to be embedded within. Those are of smaller stars that we cannot resolve, but we can detect because they are bright enough to do so. They are still putting out light. This is the Owl Nebula. It is also a planetary nebula. Again, not entirely certain why it's called the Owl. Maybe because these two stars look like eyes and it's roughly spherical in shape. Personally, I think some drugs were involved, but I don't have evidence of that. Here's a better image. One of the things that I'm constantly fighting with are friggin' satellites, which is ironic because I'm going to be a part of a project that's going to contribute to this. But yeah, from an astronomy point of view, all these damn satellites leave these streaks, and so they, in this case, they're making my picture uglier. But in other cases, if I wanted to study that star, the brightness of that star, I would have to throw out this image because of this streak that went through it. It would bias my observation. There are algorithms being developed to basically get rid of those stripes, but apparently they can't do every angle. They're apparently really or better at removing horizontal streaks than they are vertical streaks. So This one, these algorithms might be able to deal with, but this one down here, it would be a no-go. So that star, if you were looking at that star, you basically, the data has to be ignored because of that. This is M106, really pretty. It is, again, a spiral galaxy. And yes, the reason why there are a lot of spirals here is because I like spirals. Elliptical galaxies, they're kind of boring. So I prioritized looking at spiral galaxies more. You can see the spiral arm coming off of there, and then the spiral arm coming off of here. These telescopes don't have a huge or a very good angular resolution because they are small telescopes, comparatively speaking. But again, the ease of these scopes is phenomenal. If you want to get into astrophotography, particularly if you are in a light polluted environment, I cannot recommend these scopes strongly enough. Now, I am going to be putting out a review of the two scopes, a much more in-depth review of the two scopes, of the C-Star scope and the EV scope. Apparently, there's also a third one on the market that's very similar. It actually has two lenses, so maybe it gives a kind of a stereographic effect. I'm not entirely certain. I don't know really anything about that scope, but I have the access to the two scopes. What I'm hoping to be able to do is sometime soon take both of those scopes to the darkest sky I can find and do an apples to apples comparison. Basically have them look at the exact same object, create an image, and then I would just compare the two. I would also go into things like how easy is the app to use, really everything that I can. But I will give you a spoiler alert. At this point, if you had to go with the two scopes, if you had to choose one or the other, I'm definitely leaning towards the C-Star, not only because of certain features that I like that the Unistellar doesn't really do very well, but it comes down to price. The C-Star is roughly around $600-700. The Unistellar, the one I have, we got on sale, basically half price. These things run to $4,500, which honestly I don't think is warranted. The $2,000 range that we paid, that's much more reasonable. So if you were going to shell out $4,500 on one of these, I would actually recommend not doing that. I would recommend actually going into a different direction. It would be more difficult from a learning curve standpoint, but that price point is way too fucking high. I really don't understand how they can justify having that price point. Hopefully, the Unistellar folks aren't watching and coming, come after me with pitchforks. This is one of the first attempts that I made of globular cluster M53. You can see not only do you have a streak from a satellite, but it's also out of focus. That's one of the criticisms I have for the Unistellar is that the focusing procedure is not nearly as easy and straightforward as the C-Star. Oh, here we go. Stephanie, you were talking about the moon. This is with the EV scope. This is not with the C-Star. I don't know why it's appearing so damn grainy. Probably because my computer is slow. But here's the moon. Again, there we go. At least it looks non-grainy on my screen. So that's what the moon can do. There are a couple of images that I want to show specifically. There it is. These are from the EV scope. And yes, that was me looking sexy. Thank you, Norm, if you're still there. Hope you have a good one. This is the Sagittarius Cloud is an open cluster. I just love this. It's very close to the galactic center. Just the sheer amount of stars that I was able to image, the color contrast between the stars. I think it's a beautiful image, assuming that it actually ever stops being pixelated. I may, in fact, get this as a poster to put up on my wall. I don't know if it needs any more post-processing. It is just an absolutely gorgeous image, assuming it actually ever loads properly and stops being pixelated. No, I was going to wait, but again, these will be on my website, so hopefully you'll be able to see it in its better glory later on. Or if you're on my Discord, I will be posting these on Discord definitely by tomorrow morning, if not tonight, although I am kind of running out of steam. This is the EV Scopes version of the Lagoon Nebula. If you remember what the EV Scope looked like, or the C-Star looked like, this isn't exactly apples to apples. This image was taken when the Lagoon was lower down. So again, more atmosphere, more extinction. So it's not going to be as crisp as the C-Star image was. So that's why I want to do this outside. I want to do a one-to-one, have both telescopes set up, have them simultaneously look at an image, so that there is no difference in air mass, there is no difference in sky conditions, because also at this point I think it was a little bit cloudy with this one at the time. This is the Swan, if I remember correctly. It might look a little different because it is oriented different. This has to do with something known as field rotation with Alt-Az telescopes. At some point, I mean to make a video. I have lots of things that I want to make videos of. One of the things is going to be a technical kind of discussion of the advantages, disadvantages of RA and equatorial mounts versus Alt-Az mounts. One of the key problems with Alt-Az mounts is something known as field rotation, where depending on what angle of the sky, what the position of the thing in the sky, the angle of the image is going to look different. So again, a need to apples to apples. I think this is Hercules. Oh no, this is M12, another globular. All right. I think that. Yeah, that's all I got for today. Here's an image of some sunspots. That's no moon. No, if I had an image of Mimas. I don't believe I have any compromising pictures here. Hopefully I don't. Yeah, this is what the EV scope looks like. I have set it up so that I just recently, again, through the assistance of my patrons and channel members, I was able to purchase a television so that we could replace one of the monitors a monitor that we use in our control room to basically, monitor stuff, the webcams, the telescope itself. I replaced it with a television because, one, the old monitor is small, and I'm using it right now in my lab or my office. But this television allows us to actually hook in the view from this EV scope. I control it using the pad. I have a video on this on my channel. Use it controlling the pad, and then I can, from the pad, connect it to a television and show what's going on in the pad, so a larger audience can see this. So I think it'll be very useful for public events. I'm very happy about that. Yeah, I think that's it. Yeah, so lots and lots of sun pictures. All right, I think that is all I've got for, well, I don't think, I know that's all I've got for today. Thank you all for being here. Thank you all for watching. And for those of you who are watching this on Memorex, thank you as well. I am thrilled that I have the audience that I have. I'm hoping to be able to bring you more consistent content in the future. I am working on revamping my Stars and Galaxies course, which is going to be taught asynchronously this summer, starting June 24th. So I want to have lectures prepared for that. These will be shorter lectures, more pointed. They'll be about, I don't want to make them any longer than 30 minutes. And they will be focused on questions, essentially. Each lecture will be themed on a particular question, such as how do we determine the distances to stars? And then I will go over the various techniques. How do stars evolve with time? How do they change with time? And I'll go into stellar evolution, that sort of thing. So those are coming out, will be coming out fairly shortly. Well, within the next few weeks. And so, yeah. I feel bad, Maya, if you're still here. I haven't been able to check out your streams lately because I've just been, just between health and work, it's been kind of a shit show. So I'm hoping to be able to catch up on some of the back issues fairly shortly and send in my reparations. Well, actually, I'll send in Weasel's reparations. He still needs to pay me back for the rest of them. So, yeah. Which got me thinking, completely off topic, speaking of reparations, you know who needs the reparations? People who are convicted of weed, or of possession of weed as a felony. We fucked these people's lives up over possessing a drug that we are now legalizing. If anyone deserves some money for having their lives fucked over by the federal government, it's those people. At the very least, they need to have their, I would recommend that they have their felony convictions voided off their records. At least in the states where the weed is legalized. Anyway, that was a random thought off the top of my head, which has nothing to do with astronomy, science skepticism, or mental health, because that is what I, Professor Parks, PhD, make content about. If you like that sort of thing, please like, share, and subscribe. And hit that bell for notifications, because I'm a chaotic son of a bitch, and I do not post regularly at all, and frequently I will post, or I will go live pretty much at the drop of a hat if I know that I have the energy to do it and I have something that I want to say. So if you'd like to help me out, if you'd like to help out the observatory if you'd like to help out the observatory, please consider becoming one of my patrons. All monies from Patreon will go to things for the observatory, such as that television,